to Sean. In this video, we're going to take a look at a Calculus 3 lesson where we are going to find local extrema and saddle points of a multivariate surface using the second derivative test. So let's take a look at a diagram so you can see exactly what we'll be doing with the formulas in this video. So I have a diagram I want to show you. Let's take a look at this diagram first, okay? So here's a diagram of a surface in 3 dimensions, okay? So there's our x-axis and our y-axis and our z-axis. So we have a surface in 3 dimensions. We're going to be using the second derivative test to find these local extrema, the local maximum, local minimum. We're going to be these hills and valleys, essentially, of the surface. And so we're going to learn how to find these hills and valleys of the 3-dimensional surface using our second derivative test. Now, it's also, this formula is also going to find saddle points for us as well. Saddle points might be hard to see a saddle point here. It's just, you know, where you're concave up in one direction, concave down in another. So I have another diagram here that highlights what the saddle points are. This formula also finds saddle points for us. So this is what a saddle point is. So a saddle point is our 3 dimensions. So you have x, y, and z plane here. Right there at the origin, you can see in one direction, in the y direction, it looks concave up, but in the x direction, it looks concave down. So that origin right there, that's going to be called a saddle point. I mean, it looks like a saddle that you would put on if you're riding on a horse. So I think that's why they call it a saddle point. So we're going to use the second derivative test. And the second derivative test that we're going to learn here or review is going to help us find these saddle points of a surface, right? And it's going to also find the local extrema, local maximum, okay, local minimum. It's going to find the local extrema of a surface as well. All right, so the formula is, the second derivative test theorem, I should say. It's over here on the screen off to the side. So there's a D equation, okay, D equation which really is generated from taking the determinant of the second partial derivatives of your surface. So when we get to the step where we have to use this D equation, I'll explain a little bit more where it comes from. But what we want to do is we're going to take a surface here. All right, we're going to take a surface. I'm going to take you through a 4-step process. We're going to find all of our partials, first and second partials. We'll do that first, okay? And then we're going to step 2, find the critical points. We have to find our critical points, all right? The critical points is where your first partials are 0. And we'll find those critical points, because those critical points, that's where the local max, local min, and saddle points will take place, right? And so once we know where all of our critical points are, our step 3, we are going to use this equation, the D equation, and the determinant of the second partials, to determine if these critical points are local max, local min, or saddle points, and then finally in step 4 we'll find the values. All right, probably easiest to put all this to practice by, let's take a look at our example today, and these examples are a little bit more involved. So this video we're only just doing the one example. So our example here, our surface is x to the 3rd plus y to the 3rd minus 3x squared minus 3y squared minus 9x. This is a surface in a 3-dimensional plane. We want to know where the hills are and where the valleys are and where the saddle points are. We're going to find them. We're going to find them all, okay? First thing we want to do is we want to find all of our first partial derivatives and our second partial derivatives. Let's just find all of them right now in the first step, because that's what we need to get through the rest of the problem. So first thing that we're going to do first. Okay, so first we're going to find all first and second partial derivatives. Okay, so first and second partial derivatives. Okay, so that's what we do first. We're going to find all first and second partial derivatives. Let's start with the first partial derivative with respect to x. This is my way of writing. This is a cursive f, all right? So I get in the habit of writing a cursive f, so that's going to probably happen again in this video. But we want to find the first partial with respect to x. Now remember, when you're finding a partial derivative, we want to find the partial with respect to x. So you're going to differentiate all of the x terms, and you're going to let the y terms treat it as a constant. Okay, so we differentiate the x, and then the y terms are going to be constant, so they'll essentially go to 0 when they're standing by themselves. So when we differentiate with respect to x, you have 3x squared. Okay, a derivative of y cubed, but we're differentiating with respect to x, so that goes to 0. Derivative of 3x squared, so it's going to be a minus 6x. Okay, The y term goes to 0, it's standing by itself there. We're differentiating the x is the variable, so, and then derivative of negative 9x is negative 9. Then let's find the second partial with respect to x, okay? So we're just taking that partial with respect to x, differentiate that. We don't have any y's in here, so just 6x minus 6 when we find this second partial, all right? Now let's find our first partial with respect to y. All right, so first partial with respect to y, that means that we're going to differentiate the y's and the x is held constant. So x is held constant, x to the third power is treated as a constant, goes to 0. We're going to have 3y squared. So we have 3y squared here, okay? X's go to 0 minus 6y. And so here's our first partial with respect to y. Now let's go ahead and get our second partial with respect to y. Second partial with respect to y will be 6y minus 6. And then let's go ahead and get our partial with respect to x, but we want to differentiate that again with respect to y. So you take the partial, now that you don't have any y's in here at all, so because there's no y's in here to differentiate the y's, x is treated as constant, that's just going to be 0. Okay, so first thing we want to do is let's just go ahead and find all the partials. I do that first. You might want to double check, triple check, and make sure that you've got that first step done, because we need to use these in the rest of our steps, right? All right, second thing we're going to do, all right, once we have all of our partials, 5 partials, okay? 2 first partials, 3 second partials. Once you have all those lined up, second thing we want to do is we want to find our critical points, okay? So we're going to find the critical points. Okay, so how do we find that? How do we find the critical points? Okay, same way you do in Calculus 1. To find the critical points, you take your first partials, your first partial with respect to x, your first partial with respect to y, you get the zeros of the first partials. Okay, first partials we need in our, so find our critical points. Okay, so you take the first partials, all right, so 3x squared minus 6x minus 9, set it to 0. First partial with respect to y is 3y squared, all right, 3y squared minus 6y. And you're going to set that equal to 0. Take your first partials to 0. All right, and let's solve each of these. So first partial with respect to x, we have a quadratic, so you can factor out a 3. So x squared minus 2x minus 3. All right, and this could be factored further. We can take this trinomial and factor it. Let's see, so x times x is x squared. We need a negative 3 and negative 2, so minus 3 and a positive 1 is going to do that. There's x squared, and then you got 1x, take away 3x, negative 2x minus 3. So where are the zeros of this polynomial? Okay, so they're going to be a positive 3, and they're going to be at negative 1. There's the x's, okay? There's the x coordinates for our critical points, okay? So let's go ahead and get the y coordinates over here, all right? Just so happens, so in the event that you have x's and y's in both of your first partials, you'd have to solve a system of equations, all right? So you're going to take your first partial with respect to x, set it to 0. First partial with respect to y, set it equal to 0. And in a lot of cases, you got 2 equations. A lot of times, x's and y's are in both of those. If that's the case, you solve your system, solve the system of equations to get all of your critical points, okay? So let's go ahead and solve this one. So this is another quadratic. You can factor out a 3y. All right, so factor out a 3y. So y minus 2 when you factor out a 3y. When is this quantity equal to 0? When y is 0, when y is 2. Okay. So what do we have for critical points? Well, when x is 3, all right, y is 0. When x is 3, y is 2. Okay, so when x is 3, y is 0, x is 3, y is 2. What about here? Okay, x is negative 1, y is 0, x is negative 1, y is 2. So we have to include x with each of the y's, and then this x with each of the y's, and then this is what we have. So here's our critical points, okay? This is our critical points. These are our points, okay? What's happening at these points? Well, we either have a local maximum, a local minimum, or a saddle point. We have to now determine. These are our 4 points. We have to figure out what's happening at each of these 4 points, all right? So far, all right, we are finding out where the hills and valleys are of our multivariate surface. We are finding out where the saddle points are as well. We know the hills, valleys, and saddle points take place right here in our multivariate surface. This is where they're going to take place, all right? So step 1, we took all of our, found all of our partials. All right, step 2, let's get those critical points. First partials equal to 0, get your critical points. We've got 4 of them, all right? Now that we know the critical points, all right, let's determine, are they local extrema or do we have a saddle point? So step 3, we're gonna take our critical points and we're gonna figure out what they are. We're gonna classify them, okay? So your third step, all right, so the third step, the third thing we have to do is we're going to take our D equation, which is the determinant of the second partials, okay? So second partial with respect to x times the second partial with respect to y. Those are my cursive f's minus your second partial x, y, okay, quantity squared. We want to determine if these points are saddle points or if these points are extrema, okay? So we use this D equation, okay? Now where does this D equation come from? This D equation is the determinant of your second partials, right? So if I take the second partial with respect to x, and then x then y, and then y then x, and then y then y. Okay, so this is a determinant notation. So if you actually computed the determinant, remember determinant where you take this times this minus this times this, okay? So this times this, okay? So fxx, okay? Partial, second partial with respect to y, okay? Minus this times this, so partial x then y, y then x, all right? So if you take the determinant of the second partials, this times this minus this times this, we generate this equation, right? All right, so now what about the second partial x then y, second partial y then x, all right? Because they're taking it in their formula and squaring it. So we do have a theorem, Clariant's theorem, that says that if you are dealing with a continuous function, if you have a continuous multivariate function, then when you take the partial with respect to x then y or y then x, it's not going to matter, it's going to generate the same value. So because of that continuous function, then we can go ahead and we can write this as quantity squared. So your D equation is the determinant of the second partials. It's the operation that we need to use to classify our critical points. Now, if the D value, if you plug in, we're going to plug the critical points, second partials, into this D equation, we're going to get a number. If the number that we get, if the number it generates, if it's a positive number, it's a local max or a local min. If it's a negative number, it's a saddle point. That's how we're going to know which is which, all right? So if we plug these points in to the D equation, if it's negative, it's a saddle point. If it's positive, then it's an extrema. How do we know if it's a max or a min? Second partial with respect to x will determine if it's a max or a min. Second partial with respect to x is positive, your critical number is going to be a local minimum. Second partial with respect to x is negative, your critical point is going to be a local maximum. So let's go ahead and see how these points are going to work for this equation right here. So let's go ahead, so we want to take this D equation right here. This is what we have to do third, okay? We are going to take, let's start with 3, 0. So we're going to plug in 3, 0. So we're going to plug them into our second partials, all right? So we're going to take the second partial with respect to x, put 3 in for x and 0 for y. Second partial with respect to x, 3 goes in for x. There is no y's here. 6 times 3, 18 minus 6, you get 12. All right. Second partial with respect to y, we're going to plug in 3, 0. So 3 for x, there are no x's, but plug in 0 for y, you get a negative 6. All right. Minus the second partial with respect to x, then, well, that's 0, so 0 squared. So when we compute this at negative 72, that's less than 0. All right, when your D value comes out to be negative, then your critical point is a saddle point. So what is this? That we determine that this point right here, 3, 0, is a saddle. All right, so this is a saddle point right here. All right, and then we go to our next. All right, what point do we want to do next? Let's go ahead and do 3, 2. All right, let's just go 3, 2 next. All right, so you can see what it says over here on the screen. This is your theorem. All right, this is your theorem. Your D equation, you're going to evaluate your D equation at each of your critical numbers. Critical numbers are generated by taking your first partials to 0. If your D value is positive in your second partial with respect to x positive, you found a local min. If your D value is positive but your second partial with respect to x is negative, you found a local max. If your D value comes out to be negative, then it's neither a local max or a min, but note that in case C, if your D value is negative, it's called a saddle point, okay? So there's some information on the screen over here regarding this. So let's go ahead and plug in 3, 2. Okay, so we're going to plug 3, 2 into our second partials, right? So into our second partials. So second partial with respect to x, plug in 3 for x, 2 for y, and so you're going to get 6 times 3, 18 minus 6, you're going to get a positive 12. And then we're going to go to our second partial with respect to y, plug in 3 for x, 2 for y, 6 times 2 is 12, minus 6 is 6. And then we know that this is 0. Okay, so our second partial x with respect to y came out to be 0. So this is a positive 72. Our d value came out positive. It's an extrema. Is it a max or is it a min? Oh, we've got to check the second partial with respect to x at 3, 2. We got to check this. So second partial with respect to x, plug in 3 and you get a positive 12. Positive 12. So if your d value is positive, second partial with respect to x is positive, then your critical point is a local minimum. So 3, 2, our critical point here, 3, 2 is a local min. All right, so we have that. All right, so there's we still have 2 more points to go. Okay, so it's 2 to go, 2 down, 2 to go, negative 1, 0. Let's check this critical point. Check this critical point. We're going to take the negative 1, 0. We're going to plug them into our second partials. Let's take the second partial with respect to x. We're going to plug in negative 1. 6 times negative 1, that's a negative 6 minus 6 gives us a negative 12. All right, and then we want to plug that into the y. So we're going to plug in negative 1 for x, 0 for y. That gives us a negative 6. All right, and then minus our 0 squared. Okay, partial of x with then y. So negative 12 times negative 6, positive 72, it's positive. So we plugged in this point to our second partials, d equation, determinant of the second partials. We got a positive value. Positive value, we found an extrema. Is it a local min or is it a local max? Well, we got to check the second partial with respect to x, okay? Negative 1 for x and 0 for y. When we check the second partial with respect to x, plug in negative 1 for x, you get negative 6 minus 6, it's a negative 12. All right, so if your d value, determinant of the second partial's value comes out positive, but your second partial with respect to x comes out negative, your critical point is a local maximum. So our critical point here, negative 1, 0, this is a local maximum. So here's a local maximum. Just we're going to figure out the values in a moment. This is just the work that we're doing to classify them, right? Finally, negative 1, 2, negative 1 for the x and 2 for the y. Let's plug in this critical point to our determinant of the second partial's equation, d equation up here. So we second partial with respect to x, plug in negative 1, 6 times negative 1 minus 6 is a negative 12. Second partial with respect to y, we're going to plug in negative 1 for x, 2 for y. 6 times 2, 12 minus 6 is a positive 6, minus 0 squared. This is a negative 72. D value comes out negative. When the d value comes out negative, we found another saddle point. This is another saddle point. All right. So this is how we classify them. All right, so and then we need to find the values of our extrema, but this so we can see where we're at. But this is how we classify them. All right, so take a look at what we did. We need all of our first and second partials, right? Step 1, get all of your first partials, get all of your second partials. All right, so there's 5 partials to get: 2 first partials, 3 second partials. Get all of your first and second partials. All right. All right, step 2, well, why do we do that? Because we need to use our first partials in step 2 to find your critical points. We need to use your second partials in step 3 to figure out what that value is from the determinant of the determinant of the second partials. All right, so now how do we know these are the critical points? How do we know if they're maxes or mins or saddle points? You take your d equation. You take your d equation. If the value comes out negative, it's a saddle point. All right, plug your critical numbers into the d equation. If the value comes out positive, second derivative positive, you found a local minimum. Value comes out positive, second partial with respect to x negative, you found a local maximum. Now, this second derivative test, in the description below, I have a link to my video on the second derivative test from Calculus 1. So if you forgot that relationship, if you forgot the second derivative test from Calculus 1, you may want to take a quick look at that. That'll help you really understand why this part of the theorem holds true. So you may want to take a quick look at that. All right. Then finally, our fourth step is we just want to figure out where the values are for our local max and our local min. So running out of space here. So let me see if I can write the fourth step up here. Let's see if we can kind of fit it here. Okay. So we know our saddle points. We know where they are. Okay. Our local minimum. So we know we have a local minimum. At 3, 2, right? So let's, local minimum, so when x is 3 and y is 2, let's plug it into our multivariate function and see what we have. So we have 3 cubed, so 27, okay? Minus 2 cubed is 8, all right? Minus 3 times x is 3, so 3 times 3 squared, so minus 27, okay? And then 2 squared, that's 4 times 3, so minus 12, and then minus 9 times 3 is 27. Okay, so 27's cancel here, so minus 20, this is a positive 8, isn't it? Okay, so these 27's cancel here, so you have, let's see, 27 minus 12, negative 39 and a positive 8, so negative 31 is the value of the minimum. Okay, where's our local maximum? All right, so our local maximum, well, let's plug into the function. Where's our local maximum here at negative 1, 0? So let's go ahead and plug in. So negative 1 cubed is a negative 1, plus a 0 cubed is 0. Okay, 3 times negative 1 squared, so it's minus 3. Okay, minus 0 because we have 0 for y, and then 9 times a negative 1 is a positive 9. Okay, so 9 minus 3 minus 1, so 5. Okay, so those are the values, all right? So our final answer, let's see, where can I write our final answer, okay? All right, so maybe I'll squeeze it way over here, okay, for our final answer. So here's our final answer. So we have a local minimum. Our local minimum is, let's see, where's our local minimum? 3, 2, so f of 3, 2 equals a negative 31. That's our local minimum, right? We have a local max. Where's our local maximum? At negative 1, 0, negative 1, 0, the value came out to be 5, okay? And we have saddle points. Okay, and where are the saddle points? The saddle points are at 3, 0, and negative 1, 2. And there's our conclusion. Okay, so fourth, we're just finding the values for the fourth step. And then here is our final answer. Okay, so here's our conclusion. So this surface right here, all right? So this surface right here, we found the hill, we have a hill, and we found the valley, and we found the saddle points on this surface, okay? So just really quick, we're going through this one more time, because it's kind of a busy, long problem, right? So we have a surface, we want to find the hills, we want to find the hills, we want to find the valleys, we want to find the saddle points, all right? So how are we doing that? Multivariate calculus, we're going to use our second derivative test, okay? So second derivative test, pretty much a 4-step process, the way I take you through it, all right? So second derivative test involves this D equation, the determinant of the second partials, all right? So theorem proven to be true. So if your D, this determinant of the second partials, if this operation, when you plug in your critical points to this formula, if it generates a negative value, then you found saddle points on your surface, okay? And if it generates a positive value, then you found local extrema on your surface. So I, usually take people through this four-step process. Find all your first and second partials. Do that first, all right? Double check, triple check, and make sure there's no mistake there, all right? All right, then take your first partials to 0 to get your critical points. Do that next, okay? First partials to 0, all right? Your first partial with respect to x was only in terms of x, y only in terms of y. Many times you're going to have x's and y's, x's and y's. So if that's the case, then you're solving a system of equations to get your x's and y's. But make sure you find all of your critical points, okay? You got to find all of them so you can classify them. Step 3, classify your critical points. You got the critical points, you got to figure out, are they a local maximum? Are they a local minimum? Or are they saddle points? So you're going to use your determinant of the second partials formula. If the value comes out negative, you found saddle points. If the value comes out positive, Second partial with respect to x, also positive, you found a local minimum, value comes out positive. Second partial with respect to x, negative, you found a local maximum. So, and then once you use your third step here to that D equation to classify where the critical points are, fourth step, find those values, okay? Maximum, minimum, get that z coordinate, okay? So take the maximum, minimum, plug them into your function to get the x, y, z, so you can see the specific point in the three-dimensional plane, the specific point, right? It was an ordered triple if you have like 3, 2, negative 31, that's where the local minimum is. All right, negative 1, 0, 5, that's where the local maximum is. Whew, okay, so here is finding extrema, saddle points of a surface. So I hope this helps with your studies, Calc 3. So, I mean, if these videos do help, I would appreciate if you would subscribe. So anyways, thank you very much for tuning in. Take care. Thank you again.